probability for z, like between the z of negative z of alpha over 2 and z alpha over 2 is the probability 1 over alpha. Okay, so this is the probability. And we also know the sampling distribution of x bar. And based on the central limit theorem, we say the x bar, the sampling distribution of x bar will be approximately normal. Okay, and since it's approximately normal, the mean will be mu and the standard deviation will be sigma over square root of n. N is the sample size. Okay, so given these two concepts, if we put them together, we know that z is standard normal distribution, and we also know that the sampling distribution of x bar. Okay, try to recognize this phrase as one word: sampling distribution of x bar. Okay, sampling distribution of x bar is approximately normal, and the normal distribution will be mean mu and standard deviation of sigma over square root of n. Okay. Right, so we can combine these two expressions together, these two ideas together. So the x bar minus mu and divided by its standard deviation will follow standard normal distribution. And remember the process here, as we written on the board, is called standardization, right? Or normalization. We have written here the process. Mean minus its mean and divided by the standard deviation. So after this process, this is sample mean. This is the population mean. And with this expression, we will have the standard normal distribution. And given this, we can plug that value back to the first equation. Okay, so substituting z into the general probability statement about x, and we will have this expression. Okay, so let's read this set of equations line by line. Okay, so the first line is directly obtained from this slide, exactly the same. This is the standard normal distribution from last week. And the second line, okay, we just replace with this expression with the sampling distribution of x bar. Okay, and the previous one. So we just put this into this place. Okay, so we got this one. And then for the third formula, we just rearrange these items. Okay, because we have the sigma over square root of n in the denominator, and we multiply them into these three articles, three items, and we got this expression. Yeah? So it's quite straightforward. And then the last one, we just move x bar to the other side, to the double side of the in the middle. Okay, so in the middle one we have x bar minus mu, okay, and we prefer to keep mu in the middle, so we can minus x bar for all of these three, and we times the negative sign, and we will have the red equations here. So it means that, well, this gives us a very, very interesting, very fundamental understanding of the connections between mu and x bar. Mu and x bar. Okay? If we look at this formula carefully, it says that if mu is here, okay, and x bar, this is the simple mean, and we have the standard normal distribution, we have the statistical value here, and sigma is known, its population standard deviation is known, and the sample size n is also known because this is from our sample. Okay, and we have x bar plus this amount of value, or x bar minus the same amount of value, right? So it creates some kind of interval create some kind of two ends that will give us an understanding about where the mu will lie. Okay. So the x bar is a point estimator of the mu, and given that we have an understanding of the sampling distribution of x bar is normally distributed, then we can apply this logic to create an interval for mu. Yeah. Okay, so as we said, this is a confidence interval of mu, confidence interval estimator of mu. Okay. So as we can see that from this expression, we create a symmetric interval centered at our x bar, right? And we move to the left for this amount of value, and we move to the right for such amount of value, and we create an interval. And this interval will have some indication about the possible positions of mu. But this is a probability statement because we have a probability of 1 minus alpha. 1 minus alpha. So it means that there are still some room, some possibilities for us have a wrong interval. Because if we set the alpha at 0.05, it means that we will have 95% of the confidence to capture the fixed but unknown population mean. But we still have the 5% of chance to miss mean. Yeah? So, remember, as I said, we collect samples from our population, and the population statistic will change. It's variable. It will change based on our sample, right? So we are not sure which value is exactly will give us the best understanding about mu, because usually we have only one sample, have only one chance to collect a sample. Okay, so the point estimator is very risky, right? So we have to create an interval, confidence interval, so that we have a better understanding about the possible location, possible position of mu, right? But since the point estimate, our starting point x bar changes, varies, okay, it's highly likely that we will miss the actual mu, and the probability is 1 minus alpha. Okay, so this is the probability that we will get the actual fixed but unknown mu. So the probability to miss would be alpha. Okay, so that's the basic concepts about estimating mu using a confidence interval, given that the sigma, the population standard deviation, is known. Okay, so let's move forward to the further explanation. Well, this expression is the same as the last one. Okay, the fourth line, we just copy here. Right, so this equation says that with repeated sampling from this population, the proportion of values of x bar for which the interval includes the population mean mu is equal to 1 minus alpha. Okay, I use the color to indicate the corresponding part in the equation. Right, so the red one shows the interval. Okay, x bar plus and minus some certain amount, and 1 minus alpha is the proportion. Okay, why it says proportion? Because it is repeated sampling. Okay, and the other thing is, in such expression, 1 minus alpha, it is proportion of the values. It is incorrect to say it's the probability of the interval to capture the mu. Okay. The meaning of proportion and probability are totally different. Okay. If we say it's the probability of values of x bar to include the population mean, it implies that we think the population mean is variable, is unknown, and is not fixed, is variable, so that we have the probability to capture it, to include it. But in reality, it is not, because, as I said, our underlying assumption about statistic is the population parameters are fixed. Okay, so since population parameters are fixed, and what does it mean by such interval? These interval will either include these population parameter or not. It's a yes/no outcome, right? I pick up a sample, I calculate the population, or I calculate a sample mean, x bar, and I create a interval like this. Either this interval includes the unknown but fixed population mean, either not. But I have no idea because this is unknown. Okay, so the idea of this confidence interval is that the interval is either capture the unknown mu or not. But I have no idea if it's yes or no. So we said if we repeat such process, if we repeat sampling, okay, and we are confident that with a certain amount of proportion of such intervals will capture, will include this unknown but fixed mu. Yeah? Okay? So this is the meaning or the definition or interpretation about confidence interval, interval estimates or interval estimations. Okay, so we say the probability 1 over alpha, okay, is the confidence level, which is a measure of how frequently the interval will actually include mu. Okay, so this is how frequently we will include the unknown but fixed mu. Okay, so this is the very, very important idea about the interval estimation. So we have the interval can be further re-expressed like we have the lower confidence limit, LCL, to be x bar minus z over 2 and times the sigma over square root of n. This is actually the left-hand side of this expression on the previous slide. And the right-hand side of this expression is called upper confidence limit, UCL. Okay. So for short, we will put them together. We say x bar plus minus z times sigma over square root of n. Right, so to apply this formula, we just specify the confidence level 1 over alpha. So alpha is something that you have to decide. Okay, alpha is something, it's a value that you have to decide. It is the confidence level. Okay, so usually we will set at 0.05 or even or 0.01. So 1 minus alpha will be either between 0.9 to 0.99 or even higher. Okay. So alpha, this is the confidence level, and remember why it's called confidence level, because we have the confidence that if we repeat such sampling process, the proportion of these confidence intervals will capture the unknown but fixed mu will be such proportion 1 minus alpha. Okay, and as we can imagine that if we prefer to have a higher confidence, higher probability of this, the alpha must be small. Okay, when alpha be small, then the proportion of this will be higher. Right? And if the alpha has to be small, if we prefer to have a small alpha, and based on the first expression, this is derived from the standard normal distribution. With small alpha, remember the normal distribution plot, right? And if the alpha is smaller, it means that this line is either going outward, right? Because alpha is the shaded area here. This is probability, the proportion of the distribution. So if we prefer to have a higher 1 minus alpha, we must have smaller alpha. So it means that the two ends will be smaller. So it means that the width will be expanded, right? So it's quite intuitive that if we would like to have a small alpha, then the width of our interval will increase. Okay, because intuitively, if we would like to have a higher proportion of inclusion of our unknown population mean, well, intuitively we will widen our possible range so that it's more possibility to include, to capture the unknown population mean, right? So we can prove that using this kind of standard normal distribution as well. So with smaller alpha, we will have a wider width of our interval. Right. So we know this as well. So the value of this kind of interval is actually calculated by this z of subscript alpha over 2. Okay, this is actually this value. So basically, these are the normal, widely used or commonly used confidence values and a z and alpha we will use. So suppose we have 1 minus alpha to be 0.9 and alpha will be 0.1, okay? And alpha over 2 will be 0.05 and the corresponding z value will be 1.645, right? So remember, if we have a standard normal distribution like this, in the middle is 0, the mean is 0. And if the alpha here is 0.05, okay, 0.025, okay, together it's 0.05, right? Okay, so in this part it will be 1.645, yeah? Okay, and some people will like at this value is negative 1.645. Yeah. Okay, so the probability, if we look at this, the z less than or equal to negative 1.645 will be this part, will be 0.025, smaller than that. Okay, and if we have a value like this, larger than that, it will still be 0.025. Okay, and if we have a smaller alpha, these two values will be wider, will move outward. Okay, and it will be 1.96 if we set the alpha. Okay, let me slightly modify this. So this is 0.05. Okay. Right, so basically the first value of 1.645, this is the value that we will have in mind, because this value will give us the probability that the both end is 5%. Both end have 5%. And the next one is 1.96. If we set alpha at 0.05, then we will have a probability of 2.5% at both ends. And that will give us the value of negative 1.96 and positive 1.96. Okay, and if we still want to have a further smaller value of alpha, then the z value will become larger and larger. Okay, so these four sets of alpha and z values are typically or commonly used in statistics. Okay, so let's look at an example quickly so that we can integrate these ideas together. So this computer company makes its own computers and delivers them directly to customers, order them via internet. So to achieve its objective of speed, the company makes each of its 5 most popular computers and transport them to warehouses from which it generally takes 1 day to deliver a computer to the customer. Right? So in operation it's called make to order or make to stock, right? They make in advance and ship them to the warehouse closer to the customer. So such strategy requires high levels of inventory and adds considerably to the cost. Okay? You have to manufacture in advance. So to lower these costs, the operations manager wants to use an inventory model. Okay, you will learn this in SOM course. He knows demand during lead time is normally distributed, and he needs to know the mean to compute optimal inventory level. Okay. Are you taking courses in SOM? Right. You will definitely see example like this. And well, to calculate an optimal inventory policy, you have to apply statistics first. Okay? Right, so this is some kind of prerequisite for the SOM. Okay, so given this, so he observed 25 lead time periods and recorded the demand during each period. So we have the data set, XM1001 SDA. Okay, we can download it from Gmba. So the manager would like to have a 95% confidence interval estimate of the mean demand during lead time. So assume that the manager knows that the standard deviation is 75 computer. So 75 is the known fixed population standard deviation. Okay, and that is these are the 25 observations. The mean demand during the lead time. So how do we create a model based on these values? So we want to estimate the mean demand over lead time with 95% confidence in order to set inventory levels. So we have to to estimate the population mean. This is not M, this is mean, sorry. We have to slightly change the settings of. Actually, we just change to simple and it will become Greek. Okay, good. So we want to use x bar to estimate mu, and we use the formula x bar plus minus dz over 2 times sigma divided by square root of n. Okay, so actually the data I gave you or complete the calculations. So let's look at this example from Excel quickly. Right? So you have on the column A you have 25 observations, which is the same from the slides. Okay, let me make it larger so right. So we create some functions to calculate the mean, the standard deviation, and remember we have to use the stdev.s because this is simple, right? And we got the standard deviation to be 80.78, and the n equals to 25 because we have 25 observations, and sigma 75. Well, this value is fixed. Is provided by or from the problem. Okay, it's known population sigma, non-population standard deviation. Okay? It's given. And we set the alpha to be 0.05, and such setting will give us the confidence level to be 0.95. So in this case, we have the z value to be 1.96. Okay, and we can get this value from this expression, from this function, norms.s in inverse. Okay, right? So if we change the alpha, say that we change to 0.02, okay, you will see that the value changes as well. Okay, so this is a function is concurrently linked, and we can calculate this LCL and UCL and the width of the confidence interval. Okay. Right? So based on these, let's move back to our slide. Let's complete this. Right. So we can calculate this. So the estimation of the mean demand during lead time lies between 340.76 and 399.56. So we can use this as input in developing an inventory policy. Okay. So the inventory policy that we're going to learn in SOM will start from here. You have to collect sample, collect data, do some statistic work like this. And given this information, you will be able to develop an inventory policy. There are several types of inventory policies depending on the assumptions and your requirements and the frequency of decision to be made. So you'll play with it later on. So that is, we estimated the mean demand during lead time falls between these two values, and this time estimator is correct 95% of the time. Okay, and that means 5% of the time the estimator will be incorrect. But the thing is, when we say 5% of the time it's incorrect, it does not mean that this interval is incorrect or not. We have no idea if this interval is correct or not because we have no idea of this value. But it says 5% of the time, it means that if we keep running it, keep sampling, keep looking at these 25, keep taking 25 samples and do this process again and again and again, then we will have 5% of them to miss the unknown population mean. Okay, so incidentally, the media often refer 95% figure as 19 times out of 10. Okay, so in the long run, if we keep doing this, we'll have the confidence of getting it right. Okay, so this is the first example that we discussed. So it's about 8 o'clock. We may have it's time for a break, right? So let's take a break for 15 minutes, okay? And play with the example one I gave you in Excel so that you have a understanding. Try to play with these numbers. Okay, I'll come back in 15 minutes.